Nyquist. Yeah. Yes, nothing. No one should run unaccounted. Okay, where am I? Yeah. Recording started. Second, I'll publish link in a learning system. Maybe. Yeah, it's possible. Everything is possible. Lecture 11. This one, okay. Fine. Okay, let it be. This one is okay. And I hope this will be okay. Right. Yeah. What I have for today? Small demo. I have a signal source. Very good signal generator. Its distortion level below 1 in 1,000. It produces quite pure sine. I have this generator attached to a scope. This is my nice scope, but this is digital scope. This scope performs what? Sampling. It creates a table of signal, I from 1, and values, I don't know, 1 volt, 2 volts, and so on. So, in fact, my scope draws signal as a function of discrete time. Scope is able to take 2.5 gigasamples per second. It's quite a high number. One more student to account. One more student to account. So, frequency of signal is 10 kilohertz. It's a nice sign. You see, nice sign, everything fine. I will change the time scale of the scope. Take a look. 200 microseconds, 400 microseconds, 1 millisecond, 2, 4, 10. Frequency. A bit higher. This is fine, 10 kilohertz. change. More. Something changes. 400 milliseconds. Wow! And what's this? Do you see this number? 1.2 Hertz. Wait. I didn't change everything in signal. 1.2 Hertz, a nice sign. But it's 10 kilohertz signal, didn't change everything. Generator is what is it? Previous. Nice sign, 10 kilohertz. Nice sign, but 1.2 hertz. What's going on? You see, something definitely wrong. Sine 10 kilohertz. On a different time scale, hertz. How can it be? The effect, what we are observing now, it's so-called aliasing. What's the idea behind aliasing? I have an original continuous signal. Scope performs sampling. Let's say it makes and samples in parallel. This one is okay. We will see normal sine. Yeah? These points with some precision represent a signal. But what if signal is faster or scope is slower? We can face another situation. Let's say here, next one will be here. Next one here. What kind of picture will form these red dots? Very slow sine. Yeah? It's like stroboscopic effect. If we connect all these dots, we will see something like very slow sine. And we see very slow sine, 1.3 Hertz. It's an effect of aliasing. If sampling rate is too slow or distance between sampling point is too high, we feel it's a problem. It's a limitation of digital system performance. If we see something like this, sound will be distorted, image will be corrupted, and so on. We see an effect of one of the basic things, or basic ideas of digital signal processing. It's called Nyquist frequency, or result of Nyquist-Shannon theorem. Nyquist idea, it's 1938, is what if we have signal, periodic, and signal highest frequency, if something like F maximum, sampling rate or discretization frequency, F sampling should be at last twice that Mach frequency. So we need at last 2 points, but not on the base of signal period. No, 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 no. If we can decompose or represent our signal with the Fourier law, we will have base frequency, double, triple. We should have at last 2 points on the highest of the frequencies. The idea is very nice. Exactly the first one to tell about was Whittaker, but without good proof. Appears what first one who put a good base on this was Russian scientist Kotelnikov. But with Kotelnikov theorem was a problem. His idea became a victim of political speculation, but appears what he was the first because it's Nyquist first good publication of Nyquist is 1938 and Kotelnikov appears published in 1933. But okay, it's not a problem for Falcus. Our problem where the base for it. The Nyquist frequency, the limitation of sampling rate actually sets us a performance limit for any digital system. So it appears it's important. Where is my theory? It was here. This another one tiny moment. The first proof of Kotelnikov theory describes rho sine x divided by x, or sin x. Not general, but proof is for general. Okay, let's take a look. For example, we have a signal which can be represented with the Fourier law, infinity to infinity. It's signal spectral function, a power omega d omega. So we know spectral function for this signal. And what's important? Signal frequency area or frequency range is limited up to omega max. Since spectral function for minus omega max is a conjugate of omega max or any omega. I can write it for any omega, for any frequency. Signal frequency range will be from minus to omega max. Idea with spectral function, it's symmetric relative to 0. So all spectral function values at a positive frequency have their, let's say, reflex in a negative frequency area, but it will be conjugated. It will have minus at imaginary part. Negative sign at imaginary part. Okay, so we have signal represented with its spectral function, and frequency range is limited with omega max. So I can write what is spectral function. It's a classical Fourier transform. E power omega dt. It's a classical Fourier transform, but is 0 when frequency is below minus omega max. Not 0 omega max. And again 0 when frequency is above omega. I have signal with limited frequency range. And here is the trick. I can assume what? Gs omega is kind of signal and apply a Fourier transform on it. I can perform Fourier transform on this function. In this case, period, if we can call it period, will be double omega max. Double frequency range. It sounds quite difficult, quite rare. Perform a Fourier transform on a result of Fourier transform. This function itself is a result of Fourier transform. But from the mass point of view, it's okay. Sounds strange, but it's possible. So, I can assume what spectral function can be replaced with the Fourier rho. That's infinity to infinity. A power minus j p divided by omega max multiplied by omega. Why not? From the mass point of view, it's okay. Transform of transform. Can I find factors? Yes, why not? They will be complex. What will not collapse? So, complex factor for the harmonic number will be 1 divided by omega max minus omega maximum to omega maximum in the frequency range, omega multiplied by a power minus j p divided by omega max omega the omega. I'm replacing time with the frequency. I perform an operation in a frequency space. I will have, as a result, I will have frequency of the frequency. Frequency of the frequency. This function itself is a function of frequency. When I perform a Fourier transform, I will have it represented as a function of discrete frequency. But it will be not frequency of, let's say, of time, but frequency of the frequency. Repeating period, but in frequency space. Something like frequency square relative to time. It will be frequency of the frequency. Yeah, it's okay. I need to compare it to the, my signal was represented as 1 against double P, from minus infinity to infinity. Its spectral function as a function of frequency at power omega t, d omega. We can compare them. You see, we have something common. These parts are common, so right parts are very similar. Meaning what I can do such trick, like substitute, I will have double P divided by omega max, and my signal will be represented as function of interesting argument divided by omega max. Or if I set a sampling distance being P divided by omega max, I can replace it with double signal as a function of minus now my spectral function will become an interesting object. I will have sampling interval, sum from minus infinity to infinity, signal, now it's a discrete form, signal sampled, multiplied by a power j delta t omega. Yeah, and this can be a bit simplified. From minus infinity to infinity, s k delta t multiplied by a power minus jk delta t frequency. Now we can substitute in the original form of Fourier rule spectral function with this discrete representation. So our signal will become 1 against double P integral minus omega omega maximum, sampling interval sum by minus infinity to infinity k delta t e power minus k delta t omega multiplied by e power omega times d omega. Which can be represented one second next form. We have a samples of signal and something else. 1 second we will have a bit better representation. So it will be divided by double P sum by k minus or minus from minus infinity to infinity of integrals minus omega max to omega maximum, signal represented as a sample rate e power j omega m scar delta t d omega. Nice. This one is not solvable, but it's not easy to solve, let's say. But this form can be substituted by Kotelnikov's theory. Sin x divided by x, or sin rho. The same thing done Whittaker independently. To solve this, we need a substitution with specific rho. Idea what form like sin x by x for such function are they create an orthogonal system and may be used as a base for Fourier rho. Here we can substitute with sum from minus infinity to infinity delta divided by p sine omega max t minus delta t divided by omega max t minus delta t. So finally, with such substitution, we will obtain a form of signal. So it will be sum from minus infinity to infinity delta. What I'm doing, it's not omega, it's a sine of omega max time minus delta time divided by omega max time delta time. Very good. with such rho, there is one important moment. If you try to go forward directly without knowledge, you will get nothing. But with this rho, it's one specific thing. This one can be considered as a rho based for kind of Fourier rho where set, or maybe let's say fk not f, function like sine x divided by xk or sine of omega maximum delta t divided by omega maximum delta t. It's an orthogonal, such function system makes an orthogonal base for Fourier transform. And there is one important moment about such functions. Fk not t equals to unity when time is k double p divided by omega mass or k divided by f max. And equals to 0 at the moment you should have one double f max, something integer multiplied by 1 divided by f max. It's important thing. It has point of unity and points of 0. So at the interesting moment it can be multiplied by k being k divided by 1 double f max. Whole Fourier rho we have only one member, and it's equals of signal value of tk. It's equals to signal value at this point. But rho represents a signal for any time. For any time. Any means any, including this time moment. If in one moment we have equality, we have proven our theorem. This means what if our signal has a frequency range up to f max, it can be fully represented with samples taken with p divided by omega max or 1 divided by double f max. Here is conclusion. It's a proof of Nyquist theory. What? If you have signal with frequency range up to f maximum, it will be fully represented or will have take no distortions if sampling rate is sufficient to make a space between sampling points no greater when P divided by omega max by 1 divided by double frequency. So, sampling rate should be at last twice of signal maximum frequency. If not, everything will fail. This means that for any digital processing system, you have signal, you have block of analog to digital conversion, and later from there you will have digital form. But in the middle, you need a low pass filter ensuring what? All frequencies above Nyquist frequency are suppressed. Otherwise, you will get something useless. And on the other hand, Nyquist frequency sets for you what? Basic, let's say baseline or basic requirements for your system performance. If you want to record, for example, some sound with frequency up to 15 kilohertz, what? You need a sampling rate of 30 kilohertz. Actually, for sound, it's 44 kilohertz for good quality. And we can take a look on another let's go back. Oh, nice signal. My scope is a bit smarter. Than I. one is, I think it's okay. I need to switch. Wait, I think it's okay. Another experiment. What's going on now? My scope is a bit smarter than I. So it can perform a Fourier transform on a signal. I have an input of pure sine. Output, input is a yellow line, output is a red line. It's a result of Fourier transform. It should be my signal as a function of frequency. But it's a result of discrete Fourier transform, not simple Fourier transform. Can you say, what should we see? Hey, God. God, you go. We have a signal O max, let's say cosine of omega 0 time. What should be a result of Fourier transform of this signal? Any idea? I should get something like T O max multiplied by delta function omega minus omega 0 plus or minus plus delta function of omega plus omega 0. I'm observing only positive frequencies. Meaning what? What should I see? Let's say I'm watching real part of what should I see? I should get a delta function omega minus omega 0, meaning ideal, like needle. one spectral line. You have optics in school with spectrum. And device like this. Huh? Something familiar? Never saw? Spectroscope. What kind of spectrum we get if we have one ideal color? One ideal line, yeah? We have one near ideal sign on the one frequency. What should we get? One ideal line. And we're getting this red figure. Yeah, you see? Take a look what's going on frequency change. It was a good one. This is the best result, and this is the worst result. Where is ideal thin line? It should work like spectroscope. Guys from the internet, do you know what spectroscope is? You know what is it? White line becomes spectrum, but it's not white. If it's contained, for example, this lines use mercury. It will have a line for mercury. Sodium, street sodium lamps, you will see nice sodium lamp. Helium, neon, and so on. Yeah. For real light, you will see, let's say, mountains or nicely visible lines for elements, and other will be less active or something like a background. Yeah, some. Yeah, it works. So, where's the problem? Why? Why I'm getting this instead of ideal spectral line? Watch, put it toward to the lamp. Why? Should be line at omega 0, but I'm getting something like this in best case. No, problem is different. Give me one moment, I'll show. What's going on? Problem is deeper. If it would be something on the background, it would be nice. But this generator is real good. It has distortions level below 1 in 1,000. I can switch to 1 in 10,000. It's for testing of higher class of acoustic. Its output signal is really pure. No problem is in the base. It's like, say, Picadam original of discrete Fourier transform. Okay, 1 second, let me speak. For example, we have an original signal. It should be periodic. Let's say it's a pure harmonic. For example, it's a cosine of omega 0. Ideal pure signal. If we perform a Fourier transform, we will get the signal represented in a frequency space. It should be P max multiplied by delta function of omega 0 plus delta function of omega plus omega 0. In general, we should receive a delta function omega 0. That's what should we receive. As a result of ideal Fourier transform, we should get one spectral line because it contains only one frequency. But there is a problem. Time is 0 of time. Can we observe signal in infinite time? No. Here is the start point and here is the end point. 100, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 millisecond. The observation window now is 1 millisecond. We do not see signal in all time. We have started at some 0 and the end we observe only within some time frame. For my scope, here is the scope 0 time, and here plus 1 millisecond, everything ends. Here ends memory of the scope. Table of signal values inside scope's memory represents not a whole signal in its infinite time, but only cutoff, in my case 1 millisecond, of the whole signal. So we observe signal which is 0 when time lower than 0, original signal time 0 plus observation window, and 0 when time is greater than 0. We perform a Fourier transform not on original signal, but on cutoff from it. We can say what signal under transformation is a multiplication result of original signal and some kind of windowing function. Not some kind. This windowing function is simple. We we have the function 0 when time is before start time, 1 time t0 plus and 0 when time is 0. We don't have here, there is no signal for the scope. Okay, so it's a clock. It's not a signal. And nothing about this line. Below this line. After this point. Here for scope, here times ends. So we will see result of Fourier transform on time or Fourier transform on original signal multiplied by observation window function. Good. If we perform a Fourier transform on original signal, we will get a 0 as a function of frequency. Same thing if we perform a Fourier transform on string function, we will get it's represented as a function of frequency. Fourier transform on original signal multiplied by given function will be a convolution of above mentioned transform. It will be convoluted with convolution. For example, if you have 1 from time and 2 from time, the convolution, this is time function, will be from 0 to time minus tau delta tau. It's a convolution result. In our case, convolution of from omega by the function will result from the first one. It will be delta function 0 I can omit a scale multiplied by convoluted with a result of Fourier transform on Bindering function, or omega minus omega 0, because delta multiplying or convoluted with the delta function, not important, results what? Results nothing else when a delta function so Fourier transform on a 0 from time multiplied by window function results results a convolution of the, sorry, here should be frequency, of the spectral representation, or as a result we will see a frequency representation or spectral function of the observation window at a frequency omega 0. Red line is not a spectrum of the yellow signal. Red line is a spectrum of observation window. It's a problem of discrete time Fourier transform. I used a special very pure sign, and for very pure sign I got pure spectrum. It's a rare part of the episode. I should read manual. It shows it real part. It's double real part equals to absolute value. So the red line is nothing else but shifted spectral function of observation window. Really? So I should get unexpected delta function of omega minus omega 0, but I'm getting a representation of the spectral function. In theory, absolute value should look like this. It's a result of Fourier transform of t, but shifted. It shifted towards omega 0. Here is omega 0. It's an absolute value. I think it's showing me real part because see, it goes negative. Pure theory, this side lobe should be positive. If it shows absolute value. This one shows real. Okay. In general, I can tell one thing. This distance will be for p divided by even. Now, wait 1 second, I'll show it. I have time. So, let's see. I have white signal as a function of time. I'm performing a Fourier transform inside observation window with the time span of t weeks. I have points 1, 2, this one, the last one, and -1, and so on. So I'm making an n capital measurements inside observation window. So I have, let's say, signal as a function of n, and starting from 1 and ending to n capital. if I perform a Fourier transform of it, I will get some spectrum. So signal will be function of some k delta omega, let's say, where from 0 DC regime to n minus 1. In time space, some signal with the n capital measurements within an observation window will appear as a number of spectral lines, and this number they will have frequencies from 0 DC regime to n minus 1. Sampling rate. Here I have sampling rate delta equal to double P divided by discretization frequency. So whole time span of the window and multiplied by sampling rate of double N P divided by discretization frequency or sampling frequency. Sampling distance in the frequency space will be double P divided by sampling interval, not sampling interval, but observation interval defines frequency scale or frequency grid for the real analysis. My scope or any system using discrete time Fourier transform will have a frequency grid starting from 0, ending n minus 1, and space between line is double P divided by observation window. If I have signal, for example, I have a good result. Let me clean my window. Yeah. It's kind of translation window. This is frequency scale. 0, first, blah, 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 and minus 1. Double P divided by dV. Again, here is the frequency grid of my instrument. Let's say I have a good case. Omega 0 corresponds to one of the frequency scale positions. In such case, I will have good one. For absolute value, what I'm right. This line is an absolute value of sin omega divided by k omega. And the central lobe of result will be 4p divided by. This is good. Now we see good case. Can be a bad case. When there will be a bad case? Frequency of signal 10 kilohertz, exactly match the one of the sampling multiplication of sampling frequency. There can be a bad case. Bad case. I have same thing. Bad case is when signal frequency is between grid lines of the frequency scale. In such case, I will get something like this. I will one value, second value. Let me show it. Now I will get a bad case. Here it is. Change scale. You see a double peak. See this? It's a bad case. This one is the best one. When signal frequency matches one of the grid lines of the scope. And 1 second. This one is worst case. When signal frequency is exactly between the grid lines of the instrument. Can we rely on such system? Not always. You see, system sometimes performs well, sometimes performs badly. In such case, if signal should have multiple frequencies, under this line nothing can be understood, nothing can be measured, nothing can be recognized. It's a problem. And let's say base of this problem is nature of the signal we transform. We do not perform a transform on signal, but on whole signal, but on the some cutoff of the signal. We can play with observation window. Good case. Yeah, this one is good one. Take a look what changes if I change a length of observation window. See what happens. Closer and closer to needle. Because this one is 4p divided by TV. I check the longer observation window, the better frequency resolution. Even on bad case, here, bad case. Signal frequency is between natural line of of my instrument. Make a switch. Take a look, I'm changing the observation window. You see? It performs better. So the longer observation window, the more samples I took into Fourier transform, the better is result. But what means elongation of observation window? System becomes slower. And you want to record a transient, you want to record a sound. What will you get? This transformation is a base of all MPEG conversions. You will get some kind of average. So elongation of window is good for stationary signal. But when we need to deal with transient, it will not only slow down, it will smoothen transients. We will get a result of something average. Where to go? Better result. There is an idea. Why do we have this line? Because we have a sharp change in window function. Why we have sine x divided by x? Remember Gibbs function? Yes. Sharp changes. If these changes will not so sharp, maybe we can take another windowing function with smooth and with not so sharp change. This means what in common result, windowing function will play a lesser role and bigger part will go to the signal. Let me push a button. I set Fourier transform window to something under name Hamming. Hamming. What's mean? Where is my table? Hamming, where are you? It's a sign. Oh, here it is. Now, windowing function. I have for Hamming 52 minus 0.46 cosine of double P n divided by -1. I have this windowing function. You see? Much better. What kind better? This part is wider when on a best rectangular, but it less dependent on the frequency. And this baseline is lower. Actually, switch to Hamming window. Avoid Hamming. This normalized line for rectangular, but in normalized it's related to the peak point. For rectangular window, it's only -14 decibel. Now it's below 40, -42. So applying this kind of window, I got this baseline, or its official name, central lobe, or central frequency band. becomes wider. But this no, I see. This one is bad one. You see what the baseline is? I switch to Hamming and it goes much lower. So ability to detect small signal is better, but this part is wider. When the even I think this one is a better frequency. I have a good frequency resolution, but this part is wider. More ideas. Blackman-Harris. Another kind of special observation window. It gives me a point to measure frequency. This part is central lobe is wider. Blackman-Harris, where are you? Yeah. Here is the mass for Blackman-Harris window, and it's A0, okay, it's A0 minus A1 cosine of N double P divided by 1 cosine, yeah, it's okay, plus A2 cosine of double N double P divided minus 1. And, sorry, minus A3 cosine of 3N by double P and minus 1. Factors are A0, 3, 5, 8, 7, 5, A1, 4, 8, 8, 2, 9, and A3, 0, 0, 11, 6, 8. What did I get? In theory, my scope isn't able to perform its noise, its signal processing, let's say, path is not so well designed. In theory, this line, if you have a very good equipment, this line goes below 90 decibels. So, 1 in 10,000. So, such window allows you to operate with a very small signal. I don't know, astroscopy, SETI project. But this part is approximately 6 times wider than rectangle. Central lobe is wider, but it's for detection of very small signal in presence of a strong. What else? Hahn. I have Hahn window active. Okay, for Hahn window, now I have 1/2 minus 1/2 cosine of N double P divided by 1. It has a very good frequency resolution. This one is good for frequency detection because of this algorithm form. But this one, relative to this point, only 31 decibel. It's not so good for detection of small signal, but it's good for frequency detection. It gives a very good, it gives a good frequency resolution. What's the conclusion of this? Native problem of discrete Fourier transform caused by observation on a limited time interval. We do not perform a Fourier transform for all signal. We perform it only for some cutoff of original. We can, let's say, mitigate problems caused by this limited observation time, selecting an observation window without sharp change on edges. Like this hand window, it will help us to maintain sensitivity. This is rectangular, this is Hamming. Hamming, you see, this line is lower, so a good observation window gives us stability. Not so, the system will be not so sensitive on ratio or shift between system internal frequency and signal frequency. And we will be able to detect small signal. But yes, we pay with the frequency resolution and width of central lobe. We will see modulated signal. When we analyze modulated signal, it can be problem. I'll show you. So, for today I think it's enough. Maybe some questions? One goes here. So key moments: proper sampling rate and proper observation window. And if it's sampling rate, we have a good foundation, double of max frequency, with observation window sometimes, let's say, bit of magic or magician work is required to select a proper window, because you need to find a balance between frequency resolution and level of side lobe, so limiting detection of small signals. Yeah, I think it's okay for today. Yeah. Questions? Easy Scilab, for example. Or MATLAB, no problem. MATLAB is a bit less available, but no problem. MATLAB works very well. Okay, last chance for questions for online people. To watchers. Yeah. I'm not sure. System not showing. 2 people. Okay. I will end.